Hello and welcome to the fourth lecture on limits. So, in the last lecture we discussed about infinite limits and then we looked at some of the properties of limits with respect to sum of functions, and then we started with the product of functions. So, let me continue with that. So, last time we stopped at this theorem at if limit of f of x is infinity and limit of g of x is L, then and suppose L is non-zero, then the limit of the product function f x times g x this is equal to infinity if L is positive and this is negative infinity if L is negative. So, let me prove this for the case of L positive. So, assume L is positive, then what we have to show is that so let m bigger than 0 be given, we need to find delta positive such that mod x minus a less than delta x not equal to a. This should imply f x times g x is greater than m, right. So, first of all what we know is that since limit of g of x going to a is equal to L, by taking and L is positive. So, by taking epsilon equal to say L by 2, which is also positive, we can find a delta, let me write delta 1 positive such that mod x minus a less than delta 1 greater than 0. This implies g of x minus L in absolute value is less than epsilon, which is equal to L by 2, which implies g of x is greater than L by 2. G of x is in this case between L by 2 and 3 L by 2, but we need only this g of x greater than L by 2. So, similarly, because since limit of f of x is equal to infinity, there exists delta 2 positive such that mod x minus a less than delta 2 will imply f of x is greater than whatever positive number m 1 you take, and then again we will write what this m 1 should be. So, for that if we take, so if delta is equal to minimum of delta 1 and delta 2, then mod x minus a less than delta and greater than 0, this will imply that f x times g of x is greater than m 1 times L by 2, and what we want is that this should be greater than m. So, we choose m 1 times L by 2 equal to m, which means that m 1 should be equal to twice m by L. So, if I choose m 1 to be 2 m by L, then m 1 times L by 2 is equal to m, and this says that f x g x is greater than m whenever mod x minus a is less than delta. So, the limit of f x g x is equal to infinity. Similarly, we can prove for L less than 0. So, let me skip that part. Next, we will see what happens if L is equal to 0. So, this is more important. So, question, what if L is equal to 0? Is the limit equal to 0? Is it infinity? Is it something else? So, let us consider example. First, let us take f x to be equal to 1 by x square, x not equal to 0, and g of x is equal to say x square. So, in this case, here limit of f of x at 0 is infinity, limit of g of x is equal to 0. Also, if we multiply f x and g x, this is equal to 1 for all x not equal to 0. So, therefore, the limit of f x g x is equal to 1 in this case. So, here we see an example where the limit of f x is infinity, limit of g x is 0, and limit of the product is 1. Now, if we change this 1 by x square to, so if we change, let me write. So, by changing g of x to any constant times x square, we see that f x times g of x is then equal to c for x not equal to 0, and therefore, the limit of f x times g x is equal to the constant c. So, we see that for the product, if one is going to infinity and the other one is going to 0, the limit can be made to be any real number that we want. Again, let us see if we can make it to be infinity. Can we make it? Next example, we take again f x to be equal to 1 by x square, and g of x to be equal to x. So, here again limit of f of x is infinity, limit of g of x is 0, but f x times g x will be equal to 1 by x, for x not equal to 0, and then we see that. So, if we calculate the left hand limit of f x times g x, this is equal to negative infinity, and right hand limit is positive infinity. So, we see that in this case the left hand limits and right hand limits are not even equal, and they are infinity or minus infinity. If I take f x equal to 1 by x square, g x equal to say x cube, then the limit of f x times g x f x is 1 by x square, g x is x cube. So, the product is x, and this limit is 0. So, the limit of infinity times 0, it can be 0, it can be infinity, it can be minus infinity, it can be any real number. So, this is again an indeterminate form. Conclusion: infinity times 0 is also an indeterminate form, and the limit depends on the problem. Right. So, you should never make the mistake of writing the limit to be equal to 0 just because the limit of one function is 0. Right. You have to see whether the other limit is finite or not. Another thing is if the limit of both f x and g x are infinite, then we can say what the limit of the product is. So, if limit of f of x is infinity and limit of g of x is also infinity, then limit of the product is infinity, and the other one is if one of the limit is infinity and the other is negative infinity, if limit of f of x is infinity and limit of g of x is negative infinity, then limit of f x times g x is negative infinity, and you can have both the limits to be negative infinity. Then again the product is, the product has limit to be equal to positive infinity. This is because product of two negative number gives a positive number. Right. So, these things again you can prove using the rigorous definition, but they should be intuitively clear, because if you have f x and g x are both large positive number, then the product has to be again large positive number. If one of f x is large positive number, another is large negative number, then the product will give you large negative number, and if both are large negative numbers, then the product will be large positive number. So, that is all which this theorem is telling. But the problem is if you have one is a large positive number, another one is a small positive number, in that case we cannot say whether the product will be a large positive number or a small positive number, or it will be some other constant. So, let us summarize. So, we will write the limit forms. So, if we have infinity, one limit is infinity, another is some constant, then this is always equal to infinity. We have minus infinity plus any constant, then that is equal to minus infinity. Note that these are just notation to say that if the limit of one function is infinity, another is a constant c, then this sum is infinity. Similarly, the limit of one function is negative infinity, limit of another function is a constant, then the limit has to be negative infinity. Infinity plus infinity, this gives infinity, minus infinity, then minus infinity, that will give you minus infinity, and if I have infinity times infinity, this is equal to infinity, infinity times minus infinity is minus infinity, minus infinity times minus infinity is equal to infinity. So, in these cases the limits are determinate, these are given to be equal to this. Also some indeterminate forms. We have seen that infinity minus infinity, this we cannot say what it is. Similarly, 0 times infinity, this is an indeterminate form. Also 0 by 0, this we have seen previously, that if the numerator and denominator the limits are both 0, then the limit of the quotient, this depends from problem to problem. It can be a real number, or it can be 0, or it can be infinity. Infinity by infinity, that is again an indeterminate form, and later we will see some more indeterminate forms. So, let me give one example of where the limit is infinity for trigonometric functions. I am sure you have seen trigonometric functions. So, one example is what can we say, limit of tan of x as x approaches pi by 2. So, what we know is that we know that tan of x is sin x by cos x. Also sin of pi by 2 is equal to 1, and cos of pi by 2 is equal to 0. So, tan pi by 2 is undefined. So, tan of pi by 2 is not defined, but tan of x is defined in a small interval containing pi by 2, and so if we see this, another thing we know is that also cos of x is positive if x is from 0 to pi by 2, and cos of x is negative if x is from pi by 2 to pi, right. So, maybe I can draw the graph of cos of x. So, it is at 0 it is 1, so cos of x, the graph looks like this. You have 0, pi by 2, and then this is pi. So, cos of x, cos of pi by 2 is 0, and it is positive when you are in the interval from 0 to pi by 2. It is negative when you are from pi by 2 to pi. In fact, till 3 pi by 2 it is negative. So therefore, the limit of 1 by cos x as x goes to pi by 2 from the left hand limit of 1 by cos x, this will be equal to positive infinity, and the right hand limit of 1 by cos x, this is equal to negative infinity, and the limit of sin of x at pi by 2, this is equal to 1. So, by the product rule we know that, so therefore, the left hand limit of tan of x, this is equal to infinity, and the right hand limit of tan of x is equal to negative infinity. This you can also see from the graph of tan of x, which is not defined at this pi by 2, and from 0 as you go to pi by 2 it goes to infinity, then again it is 0 at pi, and this side it goes like this. Right. So, at pi by 2, if you approach pi by 2 from the left, then tan of x becomes a larger and larger positive real number. So, tan x goes to infinity as x goes to pi by 2 from the left, whereas if you approach pi by 2 from the right, then tan of x becomes larger and larger negative number. So, the limit of tan x, the right hand limit of tan x at pi by 2 is equal to negative infinity. Similarly, you can write for cot of x, cotangent x, secant x, and cosecant x. Okay, so the next thing I will talk about is what do we mean by limit at infinity. So, limits at infinity and minus infinity. So, suppose f of x is a function which is defined for for x greater than m or some m positive, if it is defined for all x bigger than m, then we can talk about the limit of f of x at infinity. So, we say limit of f of x as x approaches infinity, this is equal to L if given any epsilon positive, there exists a positive constant, there exists a k positive such that mod of f x minus L, this is less than epsilon whenever x is bigger than k. Right. So, limit at infinity just means that this is limit at x equal to infinity is a number L if you can make f of x to be arbitrarily close to L whenever x is very large. Right. So, here L is a real number. So, similarly, we say limit of f of x as x approaches negative infinity is equal to L, a real number, if given epsilon bigger than 0, there exists some negative number n such that x less than n implies f of x minus L in absolute value is less than epsilon. Right. So, the picture looks like this. Suppose we have some L here, this is our y equal to L, and then if I choose any epsilon and then if I take L minus epsilon to L plus epsilon, and we would say that the limit of f of x at infinity is equal to L provided there exists some k here such that whenever x is bigger than k, f of x should be between L minus epsilon to L plus epsilon. So, this is k, and the function, it can be something like this. In this case, we will say that the limit is equal to L. Similarly, at negative infinity means if you have, there exists some n such that before this n the function has to approach this L as, right. So, given any epsilon, you can choose this n such that the value of the function it can be anything here in between. So, this is what it means. Now, let us see by some examples. So, one is simply if we take f x equal to x, and what is limit of f of x, and limit of f of x as x goes to infinity. Let me not write this. So, let me take f of x equal to 1 by x. So, what is the limit of f of x as x goes to infinity? Claim. So, what happens if you take f x equal to 1 by x, then if you take x to be a larger and larger positive real number, then 1 by x will become smaller and smaller, right. So, that means that if you take any positive, however small positive real number, you can make 1 by x to be smaller than that. So, this limit of f of x should be equal to 0. Let us try to prove it rigorously. So, to prove this, what we have to show is that given any epsilon, so let epsilon bigger than 0 be given, then we have to find a k such that if x is bigger than k, then f of x is less than epsilon. So, if we take k to be equal to 1 by epsilon, then x bigger than k equal to 1 by epsilon, this implies that f x, which is 1 by x, has to be less than epsilon, that is mod of f x minus 0 So, f of x is equal to 1 by x and minus 0, that is equal to 1 by x, and because we are taking x to be bigger than a positive number k. So, f x minus 0, this is less than epsilon for all x bigger than k. Hence, the limit of f of x, x going to infinity, is equal to 0. Similarly, limit of 1 by x as x goes to negative infinity, this is again 0. Note that if x is a negative real number, then 1 by x is always negative, but then it becomes a smaller and smaller negative. So, it becomes a negative real number, but very close to 0. So, this is also true. Now, let us combine these two things. So, combining the definitions, so we have seen one is the definition of limit being infinity, and another one is the limit at infinity. So, combining the definitions of infinite limit and limit at infinity, we can define limit of f of x as x going to infinity to be equal to infinity if given any m bigger than 0, there exists some k bigger than 0 such that f of x is bigger than m for all x bigger than k, right. So, we say that the limit of f of x at infinity is infinity if for any large value of x, the value of f of x is large. Right. Similarly, we can define the limit at infinity to be minus infinity or limit at negative infinity to be infinity. Similarly, one can define limit f x, x going to infinity equal to minus infinity, and limit x going to negative infinity of f x equal to infinity, and limit x going to negative infinity of f x equal to negative infinity. So, example, if we take f of x equal to x and limit of f of x as x goes to infinity, this is equal to infinity, limit of f of x as x goes to negative infinity, this is equal to negative infinity, right, because we have f x equal to x. So, if x is large positive number, then f x is also a large positive number, and if x is a large negative number, then f of x is large negative number. If we take g of x equal to x square, then here the limit of g of x as x approaches infinity, this is equal to infinity, and this is also the limit of g of x as x approaches negative infinity. But let us see some limit at infinity that does not exist. So, question, limit of say sine of x as x approaches infinity equal to what? So, recall that sine of x is a periodic function and sine of any m pi, this is equal to 0 for all integer m, and sine of, if we take any 2m pi plus pi by 2, then this is equal to 1 again for all integer m. So, now if we see here what happens if sine of x to determine the limit of sine of x, what we have to see is that what happens to this function as x becomes larger and larger. But what we see is that this function you have x equal to 0, pi, and then 2 pi, and then this keeps repeating, right. So, no matter how large x you take, sin of x keeps oscillating between negative 1 and 1. This is 1, this is minus 1. So, in this case, since sin of x keeps oscillating between negative 1 and 1, in any interval of length two pi, we see that the limit of sin of x as x approaching infinity, this does not exist. So, this is an example where the limit of function at infinity does not exist, right. So, here no matter what value of L you take, you cannot make the function to be between L minus epsilon to L plus epsilon by choosing x to be large, because you know that the function will take all the values between negative 1 and 1. So, no matter what L you choose, it will not be close to remain close to L for all large values of x. So, that is why the limit of sin of x does not exist. Similarly, the limit of cos of x as x approaches infinity, that also does not exist. Similarly, limit cos of x, x approaching infinity, does not exist. Again, some properties. So, suppose limit of f of x as x approaches infinity is equal to L1, and limit of g of x, x approaches infinity equal to L2, where L1 and L2 are real numbers, then limit of f x plus g x at infinity is equal to L1 plus L2. So, this is just the sum rule for the limit at a point A. If the limits are finite L1 and L2, then the limit of the sum of the function is sum of the limits L1 and L1 plus L2. So, this can be proved like we have shown for the other cases. Similarly, if we have limit of f of x is L1 and limit of g of x is L2, then limit of the product f x times g x is equal to L1 times L2. Also, for the quotient, the denominator should not be 0. So, if limit of f x at infinity is L1 and limit of g of x is equal to L2, where L1 is any real number and L2 is a non-zero real number. L2 is in R, L2 not equal to 0, then the limit of fx by gx is equal to L1 by L2. Right. So, here L1 can be 0, but L2 has to be non-zero for this conclusion. Now, if the limit L2 is 0, then we get indeterminate form. So, for example, let me do one example. So, fx equal to say 1 by x and gx equal to 1 by x square. So, here limit of x going to infinity of fx is 0, limit of g of x at infinity, that is also 0. What about limit of fx by gx? Fx by gx is equal to 1 by x divided by 1 by x square. So, this is equal to x, and therefore, limit of fx by gx as x approaches infinity, this is equal to infinity. But if I look at gx by fx, and this is equal to 1 by x for any x not equal to 0. Therefore, the limit of gx by fx, this is equal to 0, and by taking fx equal to say a constant divided by x and gx equal to 1 by x, we see that we have limit of f of x as x approaches infinity is equal to 0, which is also the limit of g of x as x approaches infinity, and the limit of fx by g of x. You see that fx by g of x in this case is the constant c. So, the limit is equal to c, right. So, again this gives a indeterminate form if the limit of fx and gx are both 0. Similarly, if both are infinity, we will get indeterminate forms. So, 0 by 0 or infinity by infinity are indeterminate forms. For limits at infinity as well. Similarly, if we have limit of f of x is infinity and limit of g of x is negative infinity, then we cannot say in general what is the limit of f x minus g x. So, infinity minus infinity, this is also an indeterminate form. also 0 times infinity. Okay, so what we have discussed is we have discussed so far limits at a point, left hand and right hand limits. We have seen what it means for limit to be a real number L. We have also seen some examples where limits do not exist. We have seen what it means for limit to be infinity or minus infinity. Note that infinity and minus infinity, these are not number, but we say limits equal to infinity if the function can be made arbitrarily large, and negative infinity if it can be made arbitrarily small. It can be made arbitrarily large negative number. Then we also saw the meaning of limit at infinity and limit at negative infinity. All these concepts are very useful in determining properties of the function, like to draw the graph of the function. If you know the limits at infinity, negative infinity, and where the limit is equal to infinity or negative infinity, then you can easily draw the graph of the function and also deduce certain properties about the function. So, in the next lecture, we will use the limits to define a very useful concepts in calculus, which is the concepts of derivatives of function, and we will see how to calculate derivative of function, what its physical significance is, and then we will see many applications of derivatives. Also, we will use limits to define a continuous function and then discuss some properties of continuous functions. Thank you.